today. All right, as I said, today's lecture we are going to spend this lecture on the exam one review. All right, so before I start the exam review, I would like to remind you few interesting, important information about the first exam. The first exam is scheduled on Monday, March the 1st. It starts at 7 p.m. It will end at 8:45 p.m. All right. So the folder, exam one folder, will be accessible exactly at 7 p.m. on Monday. You will have to download that exam, print it, and start writing the solution. You'll have full 1 hour and 45 minutes to, solve your exam. Once you are done with the exam, we will give you additional 30 minutes to scan and upload your exam. So your exam needs to be uploaded within this 30-minute time frame. If you are done early, feel free to upload your exam early, right? If you know all the concept, then most likely most of you will be able to, finish exam within 1 hour or so, right? So we just wanted to make sure that you have enough time to, scan and upload your document. Okay, so additional 30 minutes are given for scanning and uploading purpose. There is a penalty if you submit your exam late. So after 9:15 p.m., the regular exam submission links will disappear and late exam link will appear. All right, so this late exam link will remain open from 9:15 to 9:45 p.m. So it will remain open for 30 minutes time period. 1 point penalty per minute late, right? So meaning if you submit your exam at 9:45, then the penalty would be 30 points, right? Pretty sure that most of you will be able to upload it. All of you will be able to upload it by 9:15. But in case if it's late, be sure you upload it in the neighborhood of 9:15. Okay. Um, as I said, late exam submission link will show up at 9:16 and it will stay open till 9:45. Okay, number of problems on the exam. There will be 8 problems on your first exam. Okay, and let me give you this instruction about how we want you to upload your solution. All right. This is slightly different than your PHW submission. It will be similar, but it's slightly different. What I want you to do is following. When you go to the exam one folder, you will notice that there are 9 different links. All right. The first link is for cover page of your exam. On the first page of your exam, you fill out your information and then you upload that paper in the first link. If you don't have printer, then you can write down the requested information on a blank piece of paper and then scan it and upload it in that first link. In the second through ninth link, you will see the question number written there, right? Question 1, question 2, question 3. In the first link, you need to upload the first question solution. So technically, you will be uploading 9 different PDF files in this 9 links. All right. As I said, this process is similar, but slightly different because this one question per link is slightly different idea than what we are doing with the regular paper homework assignments. If you have any issue with uploading, just send me an email and I will be more than happy to help you out there. Most of you know that when you submit your homework on e-learning, e-learning sends you a confirmation email to your UTD email ID, right? I want you guys to check that email. UTD, this e-learning instantly send confirmation email after you upload your exam, right? Or homework or any assignment, right? So check for that confirmation email once the upload is done. I believe you can verify, you can go back and check your upload too. If there is a file that is uploaded incorrectly, you can always upload a newer version, edited version of the same file, or of if you accidentally, let's say, uploaded question number 3 into question number 2 link, uh, you can always go back and fix it. You will not be able to remove the old submission, but your new submission, the latest submission, will be graded. All right. So technically, anything, if you submit, let's say, 3 different files in the same link, the third most recent submission will be graded. All right. So that's how it will go. So if you accidentally submit incorrect file in the particular question link, and then you fix it by submitting correct file, don't worry about it. All right. So the last submission will get graded. Okay. So this is the information that I wanted to give you before we start the exam review. I also would like to mention here that if there is any difficulty that you face during the exam or after the exam in terms of uploading or scanning, just send me an email and I will be more than happy to help you out. All right. Okay. So with this information is also posted as a PDF announcement on our exam session. I also sent you an email regarding this. I want you guys to read the full set of instruction, and if there are any question, if there is something that doesn't make sense from there, just shoot me an email and I will be happy to, resolve your concern or answer any question you may have. Okay. All right. So now let's try to spend the remaining time of this lecture over review um, for the first exam. If you remember, these are the list of topics that we have covered from the beginning of the semester until the last lecture. We started our discussion with the basic operations on polynomials. We talked about factorization, rational expression. We learned how to solve linear, quadratic, and rational equations. We also talked about exponents and radicals. We talked about functions. We know how to calculate their domain, intercept, asymptotes, right? We introduced these two interesting functions, exponential function and logarithmic function. I showed you how to, simplify uh, equation involving exponents. In other words, exponential equation. We also learned logarithmic properties, and we use them to expand or condense um, any logarithmic equations or logarithmic functions. And then, if you remember, we get into the idea of calculus. We introduce the concept of limit. We talked about limit at infinity, and then we talked about continuity. These are the most recent stuff. So this is something that we have covered in the last lecture. All right. So let me go ahead and give you a brief idea about all these topics carefully. All right. If we have a time, then I will definitely go over examples of limit and continuity as well. Okay, so let's try to recall, and again, I will not go into the theory. My goal is just to recall the basic idea in terms of few interesting set of problems. Okay, so let's recall these things carefully in terms of examples. Okay, so here is the first example. Let's say we would like to perform the indicated operation and simplify. Remember, we know that we can add, subtract, multiply, and divide two or more polynomials. Very easy to do that, right? Let's try to, you know, Subtract two polynomials. Suppose I ask you to subtract 2 times 3x square minus 4x plus 5 by 3 times x square minus x plus 2. All right. It's clear how we are going to perform this subtraction. I'm going to distribute 2 over all these 3 terms in the first parenthesis. I'll distribute negative 3 over all these 3 terms in the second parenthesis. And then I will, handle the like terms. Let's do that. If you open this parenthesis, you get 6x squared minus 8x plus 10 minus 3x squared minus 3x, plus 3x minus 6. Now, consider the like terms and simplify them further. 6x squared minus 3x squared, that's 3x squared. Negative 8x plus 3x, that's negative 5x. And then 10 minus 6 is going to be 4. Done. This is really the simplification of difference of these two given polynomials. We can add them too. We can multiply as well. Let's try to recall one example of multiplying two polynomials. Let's say I wanted to multiply 2x plus 3 with 4x plus 5. Remember that FOIL type method, right? You can multiply every single entry from the first parenthesis with every single entry in the second parenthesis, and then simplify the like terms. Look, 2x times 4x is 8x squared, 2x times 5, that's 10x, 3 times 4x, that's 12x, and then 3 times 5 is 15. Looks like there are two like terms here. I can simplify them without any difficulty. All right. We can even multiply two polynomials, as I said. Pretty simple, no? Let me give you one more example of multiplying two polynomials. Let's say we have 2x minus 3 multiplied by x squared plus 2x plus 3. Okay. We are going to do exactly the same thing. You can use the FOIL type method, distribute 2x over all these 3 terms, negative 3 over all these 3 terms, and then simplify the like terms. Or you can use that distribution idea. Distribute that factor 2x minus 3 over the first term, second term, and third term. Look at this. X squared will get this factor 2x plus 3, 2x minus 3. 2x will get the factor 2x minus 3. And that third term 3 will also get the factor 2x minus 3. All right. So what I basically did is I distributed this factor to x squared, to 2x, and to 3. This is perhaps the same thing that we did with that 2. Remember, we distributed 2 to all 3 terms, negative 3 to all these 3 terms. Same way. Imagine that I replace that number 2 by 2x minus 3. All right. So I distributed this factor over every single term in the second parenthesis. I need to use distributive property one more time. Let's do that. 2x cubed minus 3x squared plus 4x squared minus 6x plus 6x minus 9. Take care of the like terms. I get 2x cubed plus x squared. Negative 6x, positive 6x is 0, and then minus 9. All right. So this is what we get. This is how we multiply two polynomials. So addition, subtraction, multiplication of two polynomials is not a big deal, right? What about the division? Well, division of two polynomials requires knowledge of factorization. Remember, factorization is a process that we apply in 3 stages. Stage 1, look for the greatest common factor. Stage 2, factorization of the form ax squared plus bx plus c, or factorization of trinomial. If this doesn't work, then you go to stage 3, which consists of some spatial factorization formulas, right? Again, my goal is to recall those ideas with you. So be sure we have to use this factorization process in these 3 stages only in the proper order, right? Look for the greatest common factor, then factorize trinomial, and then try this third method, which requires you to use spatial factorization formula. Now, in the spatial factorization formula, I ask you to remember 3 formulas: difference of 2 squares, difference of 2 cubes, and sum of 2 cubes, right? So these are 3 formulas that you need to keep in mind. Okay, with that knowledge, we can create an example that uses, let's say, 2 techniques out of 3. We would like to give you 2 examples here. Let's say factorize the following polynomials. Here is the first one. Suppose we would like to factorize x cubed minus x squared minus 20x. Okay. Idea is very clear. There are 3 terms, and I look for the common factor in those 3 terms. Between these 3 terms, 1 power of x is the common factor. Let me pull it out. Left over is x squared from the first term, minus x from the second term, and minus 20 from the third term. Okay. So I used that first technique, first stage. I took the greatest common factor out. Now that leaves me with a trinomial in the parenthesis, x squared minus x minus 20. All right. For this trinomial, I'm looking for the factors of negative 20, whose sum is negative 1. What are the factors of negative 20, whose sum is negative 4? Sorry, negative 1. It's going to be negative 5 and positive 4. If you add them up, you get negative 1. Most of you know that I can write down this factorization directly because this is a monic polynomial, right? Let's factorize it. Let me write down the factorization directly for now. In a different example, I'm going to show you one problem where the polynomial is non-monic to recall the actual idea of factorizing trinomial, which involve breakdown of the middle term into 2 terms. All right, we'll see it very soon. For now, let me just use this shortcut, right? This is a monic polynomial. Factorization could be written directly. All right. As I said, I would like to give you one more example, very similar to this. Let's say we have 9x cubed minus 25x. All right, 9x cubed minus 25x. Once again, we play the same game. We just try to check if there is anything common between all terms. Looks like 1 power of x is common. So I'm going to pull it out. Left over is 9x squared minus 25. Okay. All right. Looks like I only have 2 terms there. There is no common factor between those 2 terms. It's not a trinomial, so I can't use the trinomial factorization method. That brings me to the third technique, third stage, right? Use the spatial factorization formula. There are 3 formulas that has 2 terms in them, right? 2 formulas with the negative sign in the front, negative sign in between those 2 terms. Difference of 2 squares or difference of 2 cubes. You need to decide whether these 2 terms can be seen in form of difference of 2 squares or difference of 2 cubes. Looks like both of this term has a square root. clean square root, right? Meaning I can write both of this term as a difference of two squares. So first term, its square root is 3x, so I can write 9x square as 3x whole square. In the second term, I would write it as 5 whole square. Now, that bracket inside stuff looks like a square minus b square. I can factor it now as a minus b, a plus b. Let's do that. So 3x minus 5, 3x plus 5 is what we get. And that's a complete factorization of that um, second polynomial. All right. So now we have the idea about factorization. We can talk about division of two polynomials. Let's recall how we handle the division. All right. So here is an example. Let's say simplify following rational expression. Would like to give you two examples here. Here is the first one. Let's say we have x square minus x minus 6 divided by x square minus 9, and this is divided by x square plus 2x over x square 2x square plus 6x. All right. Let's try to divide these two rational expressions. We know that division will be handled with the help of factorization. My goal is crystal clear. I'm going to factorize every single expression in the top and the bottom, and then I will cross out the repeating factors from the top and the bottom. All right. Whatever I get as a result, that is going to be, a simplification of this rational expression. Let's first convert this division into multiplication sign. Remember, in order to do that, I will just have to, flip the top and the bottom. All right. Okay. I'm ready to factorize all these four polynomials. This is a trinomial, monic polynomial of the form ax squared plus bx plus c. Factors of -6 with some -1, x minus 3x plus 2. Difference of 2 square, x square minus 3 square. Factorization will be x minus 3, x plus 3. There are only two terms. Look for the common factor. Pull out 2x, x plus 3 is left over. There are only two terms. Look for the common factor. It's x. Pull it out. All right. Looks like I can cross out 4 repeating factors from top and the bottom. I can cross out these 4 repeating factors from top and the bottom. That really gives me 2 as my final answer, right? So again, simplifying rational expression, not a big deal, right? It requires the concept of factorization. What about adding rational expressions or subtracting rational expressions? Well, they also requires the concept of factorization. So here is an example. Let's say I have x over x plus 1 minus 2 over x minus 1 equal to 4 over x square minus 1. Sorry, plus 4 over x square minus 1. Okay, so we are talking about rational expressions. Okay, we would like to add 3 rational expressions. How do we add them? Well, we need to find the common denominator first. And once we have a common denominator, we can make it visible under every single term. And then we are going to perform this operation on the top expressions. Okay, so find out what is the common denominator. Well, For that, you need to write all the denominators in the factored form, right? So looks like that x square minus 1 can be rewritten as x minus 1 x plus 1. Look at that. Now I can see what is the common denominator. Common denominator is going to be the product of x minus 1 and x plus 1. Make it visible under all these three terms carefully, right? X plus 1 is x minus 1 is missing under the first term, so I'll multiply and divide it by x minus 1. X plus 1 is missing under the second term, so I'm going to multiply and divide it by x plus 1. And then the third term has both factors in the bottom, so third term doesn't require any mathematical operation. Time to write this as a common denominator. Look, x minus 1 x plus 1 is my common denominator. In the top I have x times x minus 1, 2 times x plus 1 plus 4. All right. We know how to, multiply, add and subtract polynomials. Let's do that. We need to simplify expressions in the top. I get x squared minus x minus 2x minus 2 plus 4 over x minus 1 x plus 1. Simplify these entries. Looks like I get x squared minus 3x plus 2 divided by x minus 1 x plus 1. As I said, you need to make sure if you can simplify this any further or not. Okay. Do we know the factors of 2 whose sum is negative 3? Answer should be yes, negative 2 and negative 1, right? Let's factorize it. X minus 2 x plus 1 over x minus 1 x plus 1. We just wanted to make sure that we end up getting the most simplified version of our rational expression. So fortunately, we get something that can be factored further, and then you can simplify it even further, right? Not saying that this will be the case all the time. These are randomly created examples. By now, it should be clear that I am writing those numbers and expression, randomly. You can create your own example and you can ask the same questions, right? So again, if the main idea is clear in your mind, then trust me, these problems will look very simple and very similar to each other. Okay. All right. So now that we have all this idea, we can talk about equations, right? We learn how to solve linear equation, quadratic equation, and rational equations. I would like to remind you each one of them with one problem. Starting with the simplest case, linear equation. Remember, difference between equation and expression should be clear. Expressions can be simplified. Equations can be solved. All right? Expressions can be simplified. Equations can be solved for the given variable. So here is the common instruction for the next three problems. Solve for given variable. Here is the first example. Let's say I have 3 times 2p plus 5 minus 2 equal to 2 times 2p plus 7 minus 5. All right. Let's say I would like to solve this for variable p. In order to solve it for variable p, I really would like to, distribute that 3 and 2 first. And I would like to simplify the like terms. 6p plus 15 minus 2 equal to 4p plus 14 minus 5. Simplify those like terms. I get 6p plus 13 equal to 4p. plus 9. Okay. All right. Now we need to solve this for variable p. In other words, I need to isolate variable p. Let's isolate it. Okay. For that, I need to send that 4p over to the left side, and I need to send that 13 over to the right side. Okay. So I will add negative 4p on both sides. I will add negative 13 on both sides. As I said, make a habit of writing it in this way only. It was our goal to move 4p from the right side to the left side. That's why we added negative 4p. All right. There is no need to write 4p plus 9 minus 4p and crossing out 4p on the right side. This was intentional move. Okay. So as I say, no need to write an additional step there. 2p minus 6p minus 4p is 2p. 9 minus 14, negative 4. Divide both sides by 2. I end up getting p equal to negative 2. And that is the solution of our linear equation. All right. Let's try to create an example where we need to solve quadratic equation. To solve the quadratic equation, I showed you two methods, right? Using the quadratic formula and using the factorization. As I mentioned, as far as this course is concerned, most of the time you will be able to solve quadratic equation using uh, factorization method. And this is our preferred method, as I mentioned at that time. So let's try to see one problem. Let's say I give you this equation, 3 times x square plus 1 equal to 2 times x plus x minus 1. So I have minus 10. Let's put minus 10 there. Again, I wanted to create something that result into, that result into nice quadratic equation. We put plus 10 there, and uh, it will give us a nice quadratic equation. Okay, let's try to solve this. I will simplify this first. Distribute 3 over both terms. Distribute that 2 over both terms. All right. Looks like we get 3x squared plus 3 equal to 2x minus 2 plus 10. Let's simplify this further. 3x squared plus 3 equal to 2x plus 8. This is going to be negative 5. Okay, perfect. Okay, move everything to the right side, sorry, left side. Subtract 2x, subtract 8. I get 3x squared minus 2x minus 5 equal to 0. Okay, this is a quadratic equation. We need to factorize it. Okay, all right. Find the factors of negative 15 whose sum is negative 2. Find the factors of negative 15 whose sum is negative 2. All right. Not difficult thing to identify. Negative 5 times 3. This is negative 15. That sum is negative 2. All right. Okay. The question is, can I write down the factorization directly? Answer is easy. No, this is not a monic polynomial, right? So I have to use that 3-line technique. Break that middle term into 2 pieces. I'm basically going to rewrite negative 2x as a sum of negative 5x and positive 3x. You see? So I break the middle term into two pieces based on those two factors. And then I group the first two terms, group the last two terms, take the common factor out. Common factor is x between the first two terms. There is nothing common, so I factor 1 out. So I converted that 4-term expression into 2-term expression. Look for the common factor. Looks like 3x minus 5 is the common factor. If you pull it out, left over will be x plus 1 in the parenthesis. Product of two factors is 0, only one of them itself is 0, right? So this tells me that I have two choices. 3x plus 5 is 0 or x plus 1 equal to 0. Both are linear equation. We know how to solve it. Add 5 on both sides. Divide both sides by 3. Add -1 on both sides. I get two solutions of the quadratic equation. Once again, keep the old method in mind because you might need it. All right. So if the polynomial is non-monic, certainly you have to break the middle term into two pieces, group first two, last two terms, take the common factor out, and then do the factorization. Okay, I get two solutions for my quadratic equation, and as I say, not really a difficult thing. Let's recall one example of how to handle rational equations. All right. If you remember, in the lecture, I showed you two examples. One example with two solution, one example with no solution. Right? In this review, I would like to give you one problem with one fake solution and one good solution. All right? Let's try to see this problem. Let's say I would like to solve this equation, x over x minus 2, x plus 2, minus 2 over x equal to 4 over x squared plus 2x. Okay, let's try to solve this rational equation. Now remember, I mentioned that there are many ways to solve rational equation. Out of them, I gave you the simplest possible way. Right? What would be the simplest possible way? Find the common denominator of all terms and then multiply every single term by that common denominator. What will that do? That will eliminate the denominator completely from your example. All right? I mentioned that this is the simplest way to handle rational equation. Let's try to recall it. I need to find the common denominator, so I'm going to write all these terms in the denominator in the factored form. This is in the factored form, that one is linear term. The only thing that I need in the factored form is that x squared plus 2x. If you factor x out, you get x times x plus 2. All right? Now, look, common denominator can be identified easily. Common denominator of all these three terms is product of x and x plus 2. What I'm saying is, if you multiply all these three terms by x times x plus 2, that will help you get rid of the denominator completely. Let's do that. I'll multiply the first term by x times x plus 2. The second term by x times x plus 2. And then the term on the right side by x times x plus 2. All right. Now it's time for us to get rid of the denominator. Look, x plus 2 is gone. X is gone. X is gone. X plus 2 is gone. Now remember that important thing. If you cross out expression involving variables from your equation, then you need to make sure that whatever you are cancelling is different than 0, right? So what we are saying is this. Yes, you can cross out x plus 2 from the top and the bottom of the first equation, but that requires this restriction that x plus 2 must be different than 0 or x must be different than negative 2. This cancellation is valid if that condition is true. Likewise, this cancellation is valid when x is different than 0. All right. So these are the two conditions that we need to perform the cancellation of expression involving variables from the bottom. Okay. And we need to keep them on a side. Let's simplify the leftover. X times x, x squared. The beautiful thing is denominator is gone now. 2 times x plus 2. On the other side, I have only 4 left. Denominator is gone. It's a quadratic equation. Let's try and solve it. I get x squared minus 2x minus 4 equal to 4. Let me move that 4 over to the other side. Add negative 4 on both sides, and that really gives me, x squared minus 2x minus 8 equal to 0. All right. Do we know the factors of negative 8 whose sum is negative 2? Answer should be yes, negative 4 and positive 2. Let's factorize it. X minus 4, x plus 2. Set each of this factor equal to 0 and solve for x. Looks like I get x equal to 4 and I get x equal to negative 2. Now this is how I want you to interpret these two solutions. These two solutions, they are the solution for this quadratic equation. That is true for sure. But are these two the solution for this rational equation too? Well, the answer to this question requires validation of your solution. All right. Look at those restrictions. X cannot be 2, negative 2, x cannot be 0. All right, x cannot be negative 2. That's something that we need to go from here to here. All right. So if x is negative 2, then we are unable to cross out that entry, right? So technically this is not possible. This is a fake solution. This is a solution of quadratic equation, but it's not a solution of original rational equation. Okay. X equal to 4 doesn't intersect with any of the restrictions. So this is a good solution. So this rational equation only has one good solution. Only one solution, and that is x equal to 4. Remember in the lecture we did two problems. One with both good solution, one with both bad solution. This is the one with one good, one fake solution. All right. And on your PHW, you had one situation very similar to this. Okay. One of these situation might show up on your exam. So be sure you recall this idea. Okay. After this, we started talking about exponents and radicals. So let me remind you how to simplify expression involving exponents and radicals. And also I would like to discuss the idea of rationalization. So here is one quick example of simplifying expression involving exponents and radicals. Let's say I give you this expression 2 times x to the 5 square root of y over z cube to the power 5, and then maybe 3 times x4 cube root of y over x4, let's say z cube over cube root of y to the power -3. Okay. All right. Again, as I said, I'm creating these examples randomly. So as far as you have the right technique, you should be able to handle any problem given to you. We simplify rational expression in 4 simple steps, right? Step 1, convert the outer negative exponents into positive exponent. All right, so if you notice negative outer exponent, turn it into positive outer exponent. Step 2, distribute the outer exponent to every single factor of the base. Simplify numbers and multiply power of powers, and then shift everything in the top, and then simplify exponents. All right, so these are the steps we are going to use. So what I want you to do first is, let's say I rewrite these two expressions in a simpler form where I convert those fancy notations into numerical powers. All right, this square root notation means 1 by 2 power, cube root notation means 1 by 3 power. So turn those fancy notation into numerical powers. Now, convert that negative outer exponents into positive outer exponent. Let's do that. To turn this into positive 3 power, I'll have to switch the top and the bottom, right? So y to the 1/3 will go in the top. 3x to the 4 z cube will be in the bottom. All right, outer exponents are positive now. Distribute that outer exponent to every single factor of the base. All right, so I'm gonna distribute that 5 power to 2 x to the 5, y to the 1 by 2, and z squared. So each factor of the base will get that 5 power. Same way, each factor in here will get that power 3. All right. Okay, now next step is to simplify numbers and multiply power of powers. Let's do that. 2 to the power 5 is 32. 3 to the 3 is 27. That is the simplification of the numbers. I simplified the numbers. Multiply power of power. I get x to the 25, y to the 5 over 2, z to the 10, and then I get y to the 1 by 3 times 3 is just y to the 1, x to the 12, and z to the 9. This is what I get. Shift everything in the top. So this number will stay. I'm shifting the exponent from the bottom to the top. So z to the 10 will become z to the negative 10, x to the negative 12, and z to the negative 9. All right, now simplify the powers, right? If two exponents are multiplied, sharing the same power, you need to add the powers. 25 plus negative 10. It's 25 minus 10, right? Y to the 5 by 2 plus 1. Z to the negative 10 minus 9. We know how to handle the fraction, right? All you have to do is find the common denominator, which is 2 in this case, make it visible under both terms, and then simplify the numerator, right? So it will be a good habit to rewrite that 1 as common denominator over common denominator. This will make computation a little faster. Look, I get 32 by 27 x to the 15, y to the 7 over 2, z to the negative 19. If nothing is said, then you can stop there. All right. If nothing is said, then you can stop right there. If the question says simplify and write your final answer with all positive exponents only, if this is the case, then you need to send that negative exponent into the bottom to make it positive. Look, 32 x to the 15 y to the 7 by 2 over 27 z to the 19. This is the final answer. If the instruction says write your final answer with all positive exponents. Okay. All right. So that's how we simplify expression involving radicals and exponents. Would like to give you one example of rationalization technique. So let's try to recall the idea. Let's say I want to simplify this expression 12 over 3 minus square root of 6 plus 4 square root 6. All right, suppose we would like to simplify this expression, this two-term expression. This is the first term, this is the second term. What I really want to do here is I would like to rationalize the first term. I would like to get rid of that radical from the denominator of the first term. And once that is done, I'm going to add 4 square root 6 to it to see if I can simplify the like terms further. Okay, so let's do that. As I said, I would solve this problem in two stages, right? So first of all, consider the first term only, 12 over 3 minus square root 6. Okay, as I said, my goal is to get rid of the radicals from the denominator. To do that, I'll have to multiply and divide top and the bottom by the conjugate of the denominator. Remember, the conjugate means the factor, missing factor from the factorization formula from the difference of two squares, a minus b, a plus b. So if a minus b is in the denominator, you would multiply it and divide it by a plus b, right? Let's do that. What this does, it will give us an opportunity to express the denominator in terms of difference of two squares. 3 square minus square root 6 square. Right? 3 square is 9. Square root 6 square is 6. And we know 9 minus 6 is really 3. So this is 12 times 3 plus square root 6 over 3. You can cross out 3 from the top and the bottom as a factor. That will give me this particular expression, 4 times 3 plus square root 6. Okay? All right. Very carefully, would like to mention here that I have two ways to write down this term. I can write it as is, or I can rewrite that same term in this form, 4 times 3 plus square root 6. The difference is clear. This one does not have radical in the denominator, which is a good thing, right? So now I will consider that full expression, 12 over 3 minus square root 6 plus 4 square root 6. I'm going to replace this by its rationalization, 4 times 3 plus square root 6 plus 4 square root 6. Distribute that 4 over both terms. Look, I have two like terms here. Add them. 4 square root 6 plus 4 square root 6 adds up to 8 square root 6. And that's pretty much it. This is how we simplify expression involving radicals. All right. So again, rationalization is a key idea. We have been using this idea into the limit. We have used this idea in the last lecture to calculate the limit involving indeterminate form, remember? So obviously, you should be able to connect this with something that we are doing currently. Okay, now let's move on and let me give you some idea about functions. All right, for functions, we know how to calculate their domain, range. We also know how to compute x and y intercept. We also know how to compute vertical and horizontal asymptotes. Let's try to recall this information with one quick example. All right, and example will be very simple and straightforward. Let's try it. Let's say I give you this function for f of x equal to x squared minus x minus 6 divided by x squared plus x minus 6 divided by x squared minus 4. For this function, I want to answer the following question. Number 1, give the domain of the function. Number 2, find x-intercept. Remember, x-intercept is the point on the graph of the function where the graph cuts the x-axis. This is a point in the form x comma y. All right, and we want to get that point. So give x-intercept. Compute y-intercept. Same way, right? It's a point on the graph of the function in the form 0 comma y. All right. I also would like you to compute vertical asymptote. Compute horizontal asymptote. And then last question would be, does the graph of this function have a hole? If yes, then give the x value. At which location the function experiences a hole. All right. Remember, all these questions can be answered very easily with our function. Let's answer them. To answer this set of questions, we start our investigation with the hole. All right. What I want you to do is factorize the top and the bottom polynomial to see if there is anything that you can cross out completely from the function. If you can cross out particular thing completely from the function, that is an indication that your function experiences a hole. Let's do that. Factors of -6 that adds up to +1 are going to be x minus 3, x plus 3, x minus 2. Factorization of x squared minus 4, x minus 2, x plus 2. Look, there is a cancellation of a factor x minus 2 in the top and the bottom of this expression. All right, there's a cancellation of a factor x minus 2. We need to say x cannot be 2. All right, once again, understand that this is how we interpret this function and this function. We are saying that these two functions are equal everywhere except x equal to 2. If you sketch the graph of these two functions, you will see that both of this function, they have exactly the same graph except for input 2. What is the difference at input 2 in both of this graph? Well, this graph, this function's graph, has a hole when input x is 2. This function's graph does not have a hole at input 2. All right. So that's why we are writing this restriction out. These two functions are equal only when x is different than 2. That means we identify our candidate for the hole. X equal to 2 is the point where the function experiences a hole. As I mentioned in the lecture, I'm going to use this version of my function to answer all these questions now. Okay, so let's do that. Give the domain of the function. What is the domain of the function? Well, domain of the function include everything except 2 and the 0 of the denominator of this function, negative 2, right? You can calculate domain from here too. Set the denominator 0. X square minus 4 equal to 0 gives you 2x values, right? Plus 2 and minus 2. These are the bad inputs that create 0 in the bottom. Well, so that gives me an opportunity to write down the domain of my function. And the domain is negative infinity to negative 2, negative 2 to 2, and then 2 to infinity, right? There are two bad inputs. At one bad input, function has a hole. The other bad input refers to a vertical asymptote, right? Okay, compute x-intercept. How do we compute x-intercept? Set y equal to 0 and solve your function for x. So I'm setting this version of my function equal to 0. You can get rid of x plus 2 by simply multiplying both sides by x plus 2. Solve this for x. I get x equal to negative 3. This is the x value where the graph cuts the x-axis. The actual x-intercept occurs at negative 3, 0. All right, be sure you write down your answer in this ordered pair notation. If you just write x equal to 3, you will lose some points. Okay, so x equal to negative 3 and y equal to 0. This is your x-intercept. How do we find y-intercept? Set x equal to 0 in your function. I'm setting x equal to 0 and solving for y. Looks like I get y equal to 3 by 2. So when x is 0, y is 3 by 2. 0, 3 by 2 is y-intercept for the graph of this function. All right. Compute vertical asymptote. How do we compute vertical asymptote? Set the denominator of this function equal to 0. Solve for x. The line x equal to negative 2 is the vertical asymptote of this particular function. Okay, so this function has two bad inputs. At negative 2, it experiences a vertical asymptote. At 2, it experiences a hole. All right, very interesting situation, right? Compute horizontal asymptote. Remember how we compute horizontal asymptote? To write down horizontal asymptote, you need to write both polynomial in form of equal degree polynomial. And then you take the ratio of those leading coefficients. Looks like this is a polynomial of degree 1, that's a polynomial of degree 1. So horizontal asymptote will be really the ratio of these two, which is y equal to 1 line. All right. Does the graph have a hole? Answer to this question is yes. The location of the hole occurs at x equal to 2. All right. I know that most of you can connect this information with our ongoing discussion of limit and continuity. Think about it. What does limit equal to 0 represent, limit equal to 0 represent x-intercept. All right. What does limit undefined represent? Limit DNE represent vertical asymptote of your function. If I ask you what's the limit of this as x approaches to -2, you would say DNE, and that DNE is really vertical asymptote. All right, that represent vertical asymptote. All right, same way. How do we find out the whole? Well, the whole represent this indeterminate form of the limit. If I ask you what is the limit of this function as x approaches to 2, right? It's an indeterminate form of the limit. You would get rid of 0 and then you would plug x equal to 2 in here. You end up getting 5/4, which is the limit of that function as x approaches to 2. All right, so understand that we can relate x-intercept, vertical asymptote, horizontal asymptote is limit at infinity. Remember limit at infinity? How do we calculate limit x approaches to infinity of ratio of these two polynomials? Well, we have three methods that we learned in the last lecture, right? Use one of them. These two polynomials, they are equal degree polynomial. The ratio gives you the limit at infinity, right? So all these ideas, they are the ideas that are related to what we are discussing now. They are really, we represented intercept, vertical, horizontal asymptote, and a whole, all of them with the concept of limit now. Okay, so now let's move on and let's talk about exponential equations and properties of log. Okay, so let's talk about exponential equations first. Let's say I would like to solve this exponential equation 2 to the x square over 64 equal to 32 to the power x. And then here is the next one. Let's say we have 3 to the 2x plus 3 times 2x plus 1 equal to 3 to the 2x plus 2. All right. Okay, let's try to solve these two exponential equations. The first one is very simple. The idea remains simple, that if you want to solve exponential equation, want you to notice that x is in the exponent, right? If you want to solve such exponential equation, all you have to do is write down both sides in form of exponent sharing the same base. And once you do that, you will have to equate the powers on both sides. And that will give you either a linear or a quadratic equation that you can solve. Okay, so my first goal is this. I notice that x is in the power. So my goal is to write down both sides in form of exponent sharing the same base. The question is, can I write down all of this in terms of exponent with base 2? Answer should be yes, right? So let's write it down. Writing 64 as 2 to the power 6, 32 as 2 to the power 5. Okay, what do we do with the power of power? We multiply, right? If you have two exponents sharing the same base, they are related with division sign, we subtract the powers, right? Look, that's the form that I was looking for, right? I express both sides in form of exponent sharing the same base. All right, and now we are saying that, you know, the powers must be equal if this is the case. So you just set the powers equal, you get the related quadratic equation, you know, factorize it and solve for x. I get x equal to 6 or x equal to -1. All right, this is one problem of solving exponential equation. Here is another problem. Think about it, how this problem is different from that. Well, this problem is different because x not only appears in the power, but then we have, polynomial involving variable x multiplied with that exponential term. That's what makes this idea a little more trickier, right? So what I recommend you to do here is, I want you to notice that the variable power of the number is the same on both sides. It may help if you break this thing down into two factors. 3 to the 2x times 3 to the 3. On the other side also you do the same thing. 3 to the 3x times 3 to the 2. Look at that. 3 to the 2x times 3 to the 2. Look, 3 to the 2x appears on both sides as a factor. Get rid of it. All right. So this example technically is simpler than that previous one. 3 to the 3 is 27 and 3 to the 2 is 9. Right? Let's divide both sides by 27. I get 1 over 3. Let's simplify this. Subtract 1. 1 over 3 minus 1 is negative 2 over 3. And then divide both sides by 2. If you divide both sides by 2, you get x equal to negative 1/3. And that's pretty much it, right? That's how we simplify, solve this exponential equation. Again, understand difference between both of them here. X was only in the power. And that's why my goal was to express both sides in form of exponent with the same base. Comparing the powers would give me linear or quadratic equation. Here the issue was different. I had variable x in the power, but then variable x showed up as a polynomial multiplied by exponential thing. So this is more complicated thing. So what do we do to handle this more complicated thing? Well, we either need to get rid of exponent or get rid of variable x from polynomial. I realized that exponent to the variable power is the same on both sides. So maybe break it down into two pieces and cross out variable part from both sides, and that will help. All right. Okay, now let's move on and let's talk about logarithmic properties. We know that log is the greatest simplifier in mathematics, and it has tremendous power to eliminate some serious computation from example, right? So let's try to see if we can use those properties. Let's say expand using logarithmic rules. Suppose I give you this expression, or maybe let's say I give you a function. Natural log of 3x to the 5 square root of 2x plus 3 e to the 2x times x plus 1 to the 7. All right. Remember how we use the logarithmic property to expand it? Well, you need to count number of distinct factors inside this log. Let's find out how many distinct factors are there. In order to count the correct number of factors, I'm going to rewrite this expression in such a way that I only have numerical powers. All right, if there is a fancy power given, I recommend you to convert it into the numerical power. Now count the factors. 1, 2, 3 factors are in the top, and then 2 factors are in the bottom. Altogether, I have 5 factors inside that complicated log, meaning I can break this log into exactly 5 pieces. Let's break it down. Natural log of the first factor in the top, natural log of the second factor in the top, natural log of the third factor in the top. The one in the denominator will show up with the negative sign, right? So natural log of the fourth factor will have negative sign. Natural log of the fifth factor will also have the negative sign. Now, shift the powers in the front. Log 3 plus 5 log x plus half log 2x plus 3 minus 2x log e. Remember, log e is 1. All right. I'm going to replace log e by 1. I get log 3 plus 5 log x plus half log 2x plus 3 minus 2x minus 7 log x plus 1. So this is what we get. All right. That's how we expand any mathematical expression using the logarithmic rules. All right. Now, looks like we are running out of time, but if you guys have a time, I would like to give you a few quick examples of limit and continuity. If you don't have a time, then we can certainly stop here. And this limit and continuity, they are the most recent topics that we have seen, and they will show up heavily on your first exam. All right. I have posted an additional practice problem set on the exam session. I strongly recommend you guys to download it and solve them carefully. All right. If there are issues, let me know and I will be very happy to go over them. Now let's actually go through some examples very quickly for the limit and maybe continuity too. So this will give you, a full idea of everything that is a part of your exam. Okay, so here are a few problems. Let's say compute the following limits. Number 1, let's say I would like to calculate limit x approaching to 2 of 2x squared plus 3 over 4x plus 5. What is the best way to understand behavior of the function when x is near to? Plug x equal to 2 into your function and see what happens, right? So I'm going to plug x equal to 2. At the moment you replace x by 2, be sure to stop writing that limit symbol. Looks like I get 8 plus 3 in the top, 8 plus 5 in the bottom. This is 11 over 13. Limit exists, it is 11 over 13. By direct substitution, I got that idea. Let's say I ask you to calculate this limit x approaching to 3 of 2x minus 6 over x plus 5. We do the same treatment. Plug x equal to 3 and see what happens, right? 2 times 3 minus 6 over 3 plus 5. This is 6 minus 6 over 8, and that's going to be 0. X-intercept for the graph of this function occurs at input 3. That's what it means, right? Okay, limit x approaching to 4 of x squared plus 1 over x squared minus 3x minus 4. We do the same thing, plug x equal to 4 to see what happens. Looks like I get 16 plus 1 in the top, 16 minus 12 minus 4 in the bottom. I get 0 in the denominator. Limit does not exist. What does this mean? This means this function has a vertical asymptote at x equal to 4. All right, that's how you can interpret those three outcomes. Now there was one special case. What if you get 0 in the top and 0 in the bottom as you plug x equal to a into your function? For example, let's say I ask you to calculate this limit x approaching to 3 of x squared minus 9 over x squared minus 2x minus 3. Plug x equal to 3 into your function and see what happens. Look, 3 square minus 9 over 3 square minus 2 times 3 minus 3. 9 minus 9 in the top, 9 minus 9 in the bottom. Indeed, an indeterminate form of the limit. This means direct substitution fails. If direct substitution works, we are good. If it fails, that means you are dealing with a whole. How do we deal with the whole? Well, use the factorization, rationalization, or algebraic simplification. Factorization is x minus 3, x plus 3. Do exactly the same thing that we did in that function example. Factorize top and the bottom and get rid of the repeating factor. That thing that you are getting rid of, that represent the location of the whole, right? Looks like I get limit x approaching to 3 of x plus 3 over x plus 2. Plug x equal to 3 now. Since the bad input has been removed, you are end up with 6 over 5, and that is the limit of your function. Prediction says your function will reach to 6 over 5 as you go closer and closer to 3 from the left or the right. Let me give you one problem for rationalization. Here is one example that uses rationalization. Let's say limit x approaching to 1 of x square minus 1 over square root of x minus 1. When you plug x equal to 1, you get 0 immediately in the top, 0 immediately in the bottom, right? For polynomial, we use factorization. For radicals, we use rationalization, right? So my goal is to make the problematic portion visible with the help of factorization and rationalization. So I factorize the top as x minus 1, x plus 1. And to see x minus 1 in the bottom, I'm going to rationalize the denominator. As I said, most of you would be able to connect this idea with the rationalization example that we did earlier. A minus b, a plus b. I get this full factorization. Look, x minus 1, x plus 1, square root x plus 1. In the bottom, square root x whole square will give me x. Minus 1 square will give me 1. Look, the problematic portion is gone. I really left with x approaching to 1 of x plus 1 square root x plus 1. Plug x equal to 1. At the moment you replace x by 1, you should stop writing the limit symbol. Look, 2 times 2. Limit exists, it is 4. All right. The last concept is the continuity. There are two problems that you will see based on continuity on your exam. One problem that requires you to read the graph and answer the question. So this will be the simplest problem on your exam. If you know how to read the graph, then you should be able to get full credit on that problem. So let me show you one problem and we will end our discussion for today. So here is the graph of some function. Let's say this graph has a hole. It has a vertical asymptote and maybe it has a jump, some sharp corner. Okay, there are 4 interesting inputs here. The first interesting input is right here. Let me label it as A. Second interesting input occurs here, B. Third interesting input at jump, C. And then this sharp corner, let's label it as D. All right? Okay. I also would like to put few points on y-axis. Let's use L1. All right, this one, let's say it is also at height L1. This one L2. This one L3. All right. Here is the set of question I would like to ask. There are three interesting inputs. X equal to A. Does limit exist? If yes, give the value. Is f of A defined? If yes, give the value. And then is f of x continuous? We know that if limit prediction and exact value matches, that's when the function can be claimed as a continuous function. Otherwise, we cannot claim it, right? So there are four inputs that are interesting for me. Input A, B, C, and D. Okay. Carefully check what's happening at A. If you approach to A from the left side and from the right side, what is the prediction? Where is your function going? Where function is going closer and closer to L1. Limit exists and it is same as L1, right? What is the exact value of the function at A? Well, exact value of the function, there is a hole at A. Exact value of the function is undefined. That's a bad input for the function. Limit exists, prediction says that we should go here. But whether or not your function is actually taking that value, that's a different story, right? Function is not taking that predicted value. So function is not continuous. All right, same way. Let's look at this point. For this point, if you go close to B from left and right side, looks like on one side function is tending towards negative infinity, from the other side it's going to be positive infinity. Limit does not exist. Exact value of the function undefined. Function is not continuous. So asymptote are really bad inputs. Okay, C, there is a jump, right? Exact value of the function is defined by that solid dot. It's L2. Does the limit exist? Left prediction takes me to L1. Right prediction takes me to L2. So limit does not exist. Function is not continuous. All right. Finally, that last one. What is the left prediction? Well, left prediction takes me to L3. Right prediction takes me to L3 as well. So limit exists, it is L3. What's the exact value? Well, exact value is L3 as well. Limit prediction matches with the exact value. Function is continuous. All right. Okay, so let me end this discussion here. Know that I already took about 12 to 13 minutes more. So let's stop here and thank you so much for staying. I want you guys to try that continuity example for function given in algebraic form. We do it in 3 steps, right? First, evaluate value of the function at the input. Then compute the limit and then check if they are equal or not. Okay. All right. So this is a good point to stop. So let me